Hello, hello. What's up, glass fibers? This is Brandon.
And this is Abe.
We are going to be doing a quick tutorial today on how to use ANSYS for a solid beam static structural like simulation. So you guys can start playing around with the program, messing with different geometries, and so we can start thinking about how we're going to design our beam. So our first step is going to be to go to the sidebar in Workbench that has all of the different tests you can run, and we're going to drag in a static structural. So that's going to be right down here. And so you're going to see like several tabs. We're going to have to fill each of these in sequentially, and then we'll eventually get to like our test. So the first thing we got to do is import our engineering data. So we'll double click on that. It's going to open up this new tab up here. And right now the default like material that ANSYS always starts you with is structural steel. Obviously we're not working with steel. Yeah, unfortunately. So we're going to have to go to engineering data sources, right? And so all of them are going to be listed in these kind of, or all the ones that ANSYS typically like comes with out of the box are listed in these groups right here. We're going to go to, let's see, where is it? Composite materials. That is going to be number 7 on this list. Double click that to open it. And then down here are going to be your options. And so we are going to choose, where did it go? We're going to do epoxy e-glass unidirectional. This is the closest to what we have. As you can see, it's unidirectional and then also pre-preg. And it's the dry option. So we are going to go with this one. We'll click add. And then when we go back to our list of engineering data, you'll see that epoxy e-glass UD was added. We're just doing a solid beam today and not like a composite simulation. So we're not going to worry about the foam core for right now. We do typically use 2 materials, which is the e-glass and the foam core. We're just going to stick with this for now, just to simplify things. So now that we have that, our next step, well, let's save our file first just to have an idea. Or just to have it backed up, I guess. All right, so next we're gonna have to make our geometry. So we are just going to do kind of a rough outline of what our beam would look like once it's completed. Oh, dude, I pressed the wrong thing. 1 second. Okay, so we have our engineering data. We are going to now do our geometry. So we're going to right click on geometry. We're going to open space claim. And then it's going to take a second to load here. So I'll be right back. All right, so it takes a second to load up, but now we're in space claim. This is going to be where we're going to like make our model. It's just like any like CAD software really. So if you're like familiar with SolidWorks or anything like that, it's sort of the same idea. So we are going to start a sketch and we're going to do it on the XY plane here. I'm going to just make it a line up here. Okay, so we will share the beam dimensions that we had for last year so you guys can make your own models, but feel free to get creative with it. We're just going to go off of what we had last year. So that was a top flange width of 3 inches, bottom flange width of 3.5, and then 2-inch high core. I mean, I'll show you once I make the model, but yeah, that is the idea.
But feel free to experiment with your own sizes or anything,
Indeed.
as long as it's within the specifications of the competition, which we'll also send
Yes,
out.
we'll send out the rules so you guys can make sure it's up to snuff there. Let's see.
Everything in here is up for change. You can even change the shape of it to a
True.
certain extent.
True.
So get creative.
All right, so we're gonna change the units here. I'm gonna do it in imperial units, just inches. It's gonna make it like, yeah, US of A. I'm a patriot. We're gonna use inches. All right. So that has got to be 3. So we're gonna dimension that to be 3, and then we're just gonna pull it over to so that the midpoint is aligned with the axis. Oops, nope. just like that. And then we're just going to go around and kind of draw our beam. We're going to give it a 0.1 inch thickness just because that's, at the end of the day, what our plies like really come out to once they're all laid up. But yeah, we're going to go for that for right now. Our core is 0.25 inches thick, so we're just accounting for that here.
Oh, no. Maybe more.
And then our core is 2 inches tall. This is gonna, this distance is just to account for the fact that our bottom flange is 3.5 inches. We'll do another 0.1 inch thickness here. Dude, I kind of hate Space Clam because of stuff like that. Perfect. 3.5 for the bottom one here. That. Beautiful. Okay, so that is the sketch of our beam. Let me just make sure everything checks out here. This should be okay. Perfect. All right, we are all good. So we are gonna end the sketch editing here, and then we are gonna do a pull in the Z direction, and that is gonna be 25.5 inches. That is just the like beam length that we had last year. And that is our model. That's like the biggest part of it. The last thing we need to add here is sketches for where the loads are going to be applied. So we do a 3-point beam test or bend test. So we're going to need fixed supports down here, and the actual instron that we use in the competition pushes down on the beam in the center. So we're going to do a couple more sketches here just to get that done. So let's align it here. Our contact surface for like the instron is going to be just a small circle. We'll do 0.25 inches in diameter. So that's there. And then for the support surfaces, it's going to be a similar thing. We'll send out the rule book again, and that has like a whole CAD like diagram of what the like supports will look like. So you can definitely go off that if it helps. But basically they're going to be 11.5 inches from the center of the beam. So let's see, I want to align it like this. And we're just gonna make some, the actual support surfaces are 1 inch thick, so we'll just make sure to do that. Yeah, it'll extend across here, and we'll just dimension it 1 inch. Perfect. And then the distance from the center of that, what's it called? The contact surface needs to be 11.5 inches from the actual center of the beam. And so we'll just make sure, oh, look at that. Wow. Right, so it's already there. So now we just need to mirror that whole design over to the other side. So we will use the mirror tool. We'll select our mirror plane to be the x-axis here. And then we just want to choose all of these entities. I don't think those warnings, hopefully those warnings aren't a big deal. Yeah, I think we should be all good. We can check just in case, but you know, I think we should be showing, oh, I don't want an angle. Yeah, all right, you know what? I don't know why it's giving me an angle here, but we're just going to get rid of that and hope that the mirror tool worked as intended. It looks decent to me.
It's good.
All right, so we're going to end that sketch. You know what? Actually, I'm gonna delete this construction line because I don't like it being asymmetrical. But yeah, that is going to be our beam for now. So we will head back to Workbench. And as you can see, the geometry box is now clicked. So the way ANSYS works is it has like all these kind of like substituent programs like space claim and mechanical and ACP, but basically like it's all tied back to your workbench. So when you update one, the other should also update. If it's not, you can click the update button and then it'll make sure to transfer everything. So that's a good like thing to do if you're ever unsure that like, your changes transferred. But yeah, it's kind of cool how it works like that. So now we're going to head into model. This is going to take us to mechanical. So I will be right back once that loads. Okay guys, so here we are in mechanical. And as we can see, our beautiful beam imported correctly. So now we're going to need to define a mesh. And in like finite element analysis, a mesh is just basically what breaks our component down into like really small parts. And then it can like do a bunch of complex calculations on those parts and give us the results that we need. So the first thing we got to do here is define a sizing. So we'll go up here, we'll add a sizing that's going to pop up right under our mesh. Every time we like edit the mesh, it's going to ask us to select a geometry. We just want to apply it over our whole beam. So this is body select right here. So we'll select the body and we'll hit apply. And so now it's purple. We can see that our mesh body sizing is going to apply over our entire model. And then we're going to set our default size to be 0.2 inches. This is sort of arbitrary. I mean, basically just the smaller like elements you have, the more accurate that your mesh is going to come out to, or like that your calculations will be. Obviously, you don't want to go too small, or else it can get pretty, I guess, laborious on your computer. But with like like the beam is pretty simple geometry, so I think it should be fine if we do 0.2 inches. Then we're going to do a meshing method. The method that we found works best so far is, let's see, where is it? Is tetrahedrons. That's been working best for us so far. So we're going to do that. And then it'll be like patch conforming method. Perfect. Okay, so we're going to update that and hopefully it'll give us a nice mesh here. Let's take a look. Okay, that is going to be our mesh. It is nice and symmetric. I don't see any like crazy weird defects in it. So we're just going to work with this. Our next step is going to be to add our forces and then define like all of our like fixed supports. So we're going to start with the supports actually. So we're going to click fixed support right up, or we'll click static structural, right? This is the program we're running. And then it's going to give us all these options up here in terms of like forces and supports to add. So we're going to click fixed supports, if it will let me. There we go. Oh. All right, 1 second. Okay, so for whatever reason, the screen recording software was like blocking me from adding a fixed support. But yeah, basically you are going to go static structural, and then up here, there's going to be all those options for your structural like loads and stuff, and then you'll do a fixed support. So we're going to make 2 of those. This is fixed support 2. We'll face select each of our little areas, and then yeah, we have our 2 fixed supports now, which is cool. So I'm going to blow up this window again. Just so you guys can see, the button is going to be right there. And now the last thing we need to add is our load. Now, if you do end up taking a look in the rulebook that we send out for the glass fiber team, yeah, category, we do have to withstand a 5,600 pound like ramped force load. So that is what we're going to design around. So let's see, hopefully it'll let me again. There we go. Perfect. And then for the face that we're going to select, we're going to choose that little circle we made earlier. Let me get over to it here. Perfect. And then Oh yeah, okay. There we go. Apply, perfect. All right, and then down here you're gonna say 5,600, not 56,000. That would be a little much. 5,600 pounds of force. And so that should be good. Okay. So now we have everything defined here. We just need to click the direction. And so right now it's pointing up, which is obviously not what we want. So we'll make it point down. Yeah, okay, perfect. And now we are going to add our tests. So we'll add, for now we'll do total deformation, von Mises stress and strain. And then we're going to give it a solve. So you're gonna go here and then you're gonna press solve. It's gonna take a second. There's gonna be like a little progress bar down here, but then you'll see that all these check marks should be checked. You're gonna go down, total deformation. That is what it looks like. It gives you a scale here. So at maximum, right at the center of our beam, it's in inches. So we're gonna have 0.03 inches of like deflection in the center there. Stress and strain, you can also let's see, generate those. So yeah, it's interesting that our max strain is going to be on the side there. That's something to look into. But anyways, that is how you are going to start developing like FEA simulations. Obviously, like if you guys have any ideas for different beam geometry, you can go into SpaceClaim and create a different beam. Mesh it the same way should work. You may need to mess around with like how you mesh it, but we're always happy to help if you guys want to like develop different ideas. But that is generally how we're going to be doing it. At least for like a solid beam. We are still figuring out how to do like a composite beam, and so we'll get back to you once me and Abe have figured that out. But for now, this should be a good way to get an idea of how different beam geometries will perform under load. So thank you guys for watching, and we will reach out very soon. See ya.
Thanks.